All right, so from warm Bangladesh, going to go to very cold places. Matthias Fuchs is up talking about Arctic coasts.
Okay, thank you. Yeah, I'm excited to be here talking again about Arctic deltas. We already had a good introduction this morning, so it makes it a bit easier. What I'm talking about is like I looked at carbon and nitrogen storage in Arctic, pan-Arctic delta sediments. And yeah, I want to acknowledge also my co-authors for this study. I work on that since like quite a long time. I started it when I was at Alfred Wegener Institute and the GFZ in Potsdam in Germany. So it's like kind of like ongoing work, always a little bit. And now actually the paper's in review. So I hope it's published soon. So Arctic deltas, I mean, we had the introduction in the morning. What is different compared to low latitude deltas? So you see here a map of like all the deltas I mapped in the Arctic. Really important, the low temperature regime. So Arctic deltas actually look like that for like up to 8 months of the year. It looks like that, right? It's frozen. And then as we heard in the morning, a lot of discharge happens with this freshet, spring freshet. So a lot of sediment is going on with the freshet already. Another thing, it's affected by sea ice in the coastal zone and then permafrost. We have here the permafrost distribution in the northern hemisphere. Permafrost, that is soil that is or should be always frozen, right? It's like always solid frozen. The carbon in there, the sediment is kind of freeze locked, not part of the active carbon cycle. Yeah, so we have this permafrost region in the northern hemisphere. All the Arctic deltas are kind of like affected by that, and also the catchments are in a permafrost environment. And I think that's important to know. Yeah, why are Arctic deltas important? I think if we with climate change in the Arctic, and I think Arctic deltas are actually at the forefront of climate change there, because we have sea level rise, we have frozen deposits, which now with climate change start to thaw. So we have a lot of ice in the ground in Arctic delta. So if this ice melts, we have a surface subsidence. And so on one side, we have surface subsidence and sea level rise. So I really think like with future sea level rise, Arctic deltas will be really important in terms of like what's going on in the Arctic and what happens to carbon fluxes there. It's also assumed that Arctic deltas store a vast amount of carbon. So that's where I come in with the study, because like some Arctic deltas are thought to be like 60 meters thick in deposits. So we have really thick deposits in Arctic deltas. Yeah, my question is then how much soil carbon and nitrogen is stored in pan-Arctic river deltas. You see here nice pictures like all like peat deposit, low decomposed peat deposits, still frozen in permafrost. So what happens if that actually thaws? But the first step is really to get an assessment how much carbon do we have in these Arctic river deltas, because we don't know. And when I started this study, we didn't even know the area of the Arctic deltas. So that was kind of the first step. So I had like basically when you do a carbon stock estimation, you need the volume of the sediment body times the carbon density that gives you like the carbon stock. But we didn't even know the area or the depth of these deposits. So I started with actually mapping Arctic deltas by hand based on Google Earth images. I mapped 211 deltas. I mean, it starts with the question, where does a delta start? Where does it end, right? I only did the subaerial part, the terrestrial part of delta. So I don't know much about the subaqueous part of deltas. So I have the area now. Then I wanted to know the permafrost distribution. So basically I overlaid this map to my digitized map just to know how much of the carbon is still frozen and how much is non-frozen deposits. Another thing, we needed the water bodies, because I assume in my study that water bodies contain no carbon, because I just look at soil carbon. So I had this product, kind of geospatial products. Then we have other parameters like ice wedge volume. There are deltas that have a huge ice body in the sediment. Again, we don't know much about like how much ice we really have. It's assumed like 5–6% of delta deposits contain of ice. So I assumed again, ice contains no soil carbon. So it was important for me like to estimate the sediment volume for later than calculating the carbon stock. Active layer depth, that's the layer on top of the permafrost that thaws out every summer and refreezes in winter. So for me, I considered that as the non-frozen part of the Arctic Delta. So you have to imagine every summer, like the top 50 centimeters, 60 centimeters thaws out is part kind of the active carbon cycle, and then it refreezes again in winter. Another thing, water depth. We have now the water area, but we don't really know how deep the lakes and the rivers are in the Arctic deltas. And yeah, it's kind of seems like simple, but like Arctic deltas are so remote that we just don't have that much data from up there. Another thing, important, deposit thickness. So we only have thickness information from 5 river deltas. So what I then did, I took this thickness information from 5 deltas and just did like a correlation with area. So my rationale was the bigger the delta, the thicker the deposit. And kind of works well for these 5 Arctic river deltas. That's the way how I could calculate the thickness of deposits for all other 200 deltas. And you might say, if you're really the delta experts, that might not be true. It might be a little bit shaky ground here. I'm aware of that, but that's all the data I had. And I actually checked it also for lower latitude deltas. You see here in red are the Arctic deltas, and in black some lower latitude deltas where I could just find values in literature. And it kind of like this relationship kind of holds true. So like the bigger the delta, in theory, the larger or the thicker the deposit. So that's kind of like how I justify like my deposit depth estimation. So yeah, so now I have everything for like calculating the sediment volume. So I know the depth of deposit. I have a frozen part, a non-frozen part of the delta. I have a water volume in deltas that I consider to contain 0 carbon, as well as the ice wedges here, which contain 0 carbon. And so I could calculate the sediment volume for each delta and then overall for all Pan-Arctic deltas. Yeah, the only thing then missing is carbon, right? I needed soil cores. And so we cored a lot ourselves in Arctic deltas and also synthesized data from literature. In total, I have 156 cores in my database now from 17 different deltas. And yeah, we have TOC values here, 1,600 carbon content values. Yeah, the problem here, you see most of the cores we have from Arctic deltas are rather shallow, shallower than 3 or 2 meters. So we would really need more deeper cores. That would be great. Here are my result slides. You see Arctic deltas, based on my mapping, cover an area of about 100,000 square kilometers. We have 57 petagrams of carbon. A petagram is 1 trillion kilograms. So it's quite a high number of carbon we have there, 3.6 petagrams nitrogen, and 2/3 of it are still frozen deposits. I want to look a bit more on these 57 petagrams. If we compare that to the northern permafrost region, the northern permafrost region stores 1,300 petagrams of carbon. 4% is stored in Arctic deltas, although they only cover an area of 0.6%, so like overrepresented. If we compare to wetlands in the United States, Arctic deltas store significantly more, although this number is only 120 centimeters. And then comparing to global tidal marshes, a study came out last year, they store 1.44 petagram, but you see here, the study kind of ends somewhere below the higher latitude. So if my study will come in here and Arctic deltas would actually add 5 petagrams on the first meter of soil only. So that shows kind of the significance of Arctic deltas in terms of carbon storage. Yeah, what we have data, we have like data only from 17 deltas, so we would need a better spatial resolution or distribution. Also the offshore part, I completely did not include at all, so there might be a lot of carbon still in that part, and deeper cores would also be helpful. My vision, my next step would be kind of what comes in, what goes out, like kind of like have a sediment budget for Arctic deltas. See here this nice picture from the Yukon Delta again. The question is really like, do Arctic deltas remain carbon sinks in future with the changing climate, right? I would love to go there and like measure, for example, CO2 and methane fluxes, but also just know how much sediment comes in, how much sediment is deposited, and how much sediment actually goes out again in Arctic delta. So it's kind of like the vision, just going away from stocks to more like really budget calculations, what happens to these Arctic deltas. Yeah, so that will then lead to the final question. Will Arctic deltas become carbon sources or remain carbon sinks? And yeah, data set will be published as soon as the paper is hopefully published too. So will be open access available. And yeah, that's it. Thank you for your attention.